Welcome to the March talk in our seminar series, which aims to provide accessible introductions to some of the most significant mathematical theorems of the 21st century. Today's talk will last about 45 minutes, followed by time for questions and discussions. Please feel free to type your questions or comments at any time in the meeting chat. And if your questions are urgent, I will tell the speaker immediately. Otherwise, we will discuss your questions at the end after the meeting. So it's my great pleasure to introduce our today's speaker, Professor Assaf Naor from Princeton University, USA. He is a world-leading mathematician known for his groundbreaking contributions in the interface of metric geometry, analysis, approximation algorithms. His work has earned numerous major distinctions, including Nemmers Prize in Mathematics, Ostrowski Prize, and Bôcher Memorial Prize, and many more. And in this talk, he will discuss the Sparsest Cut problem, explain its significance in algorithm design, and present recent algorithm for its efficient approximation, which is a culmination of decades of works. So I am now happy to hand over to our speaker.
Thank you very much for the introduction and for the invitation. And I can't see everybody, but welcome. And as Bogdan said, I'm happy to answer questions. I probably, as I'm speaking, I will not be seeing the chat. So if something is urgent, it will be, I will be interrupted by Bogdan. Okay, so I'm gonna discuss a problem called the Sparsest Cut problem, which is extremely simple to describe, but it's like an octopus. It connects to many areas of mathematics, and I will try to define everything. I will make sure to define everything in elementary without any requirement of any background. But again, stop me if something is not clear. So what is the Sparsest Cut? So it's the following thing. So it takes as input, the input is two matrices. That's called so you have an integer, and you have two matrices. C, the entries are Cij, and D, which are Dij. They are n by n matrices. So we want them to be symmetric. N by n matrices with non-negative entries. So that's what's given to us. And the goal is to compute, and I'll say what do I mean by this. The following. So what you do is you take a subset. So I'm going to minimize overall subset. So take the minimum over, I'll draw a picture in a second, minimum all of the subsets of this universe. They have to be a proper subset and not empty. Of the following. So what I do is when I have a subset, I sum I in the subset S, I called it, J not in S of Cij. And look at the ratio of the same sum with the D's. So I is in S, J not in S, Dij. And let's call this number opt. That's an optimal solution, C. So the input is n by n matrices. And I do the following question, the following thing. So if you think of the number, this is the numbers 1 to n. A subset is just some partition of this into two pieces. And once you have a partition, you can look at only the i's and j's such that, let's say this is the subset, let's say the left side here is a subset S. So I is in one side, j is on the other side. And then the numerator is just the sum of all the C values, the non-negative values, crossing the boundary. And you look at the relative to the sum of the same sum, but with a different set of weights, the D's. Okay, so And the goal is to compute this number. So, of course, that's a silly question. I wrote down what the number is. So the goal is to compute it in polynomial time. I'll give examples in a second, but just so you grasp what this means, this is a very simple quantity, what's written here, just a ratio of two numbers, but the number of subsets is 2 to the n. So if somebody succeeds to compute this in polynomial time, then in particular, that person is not going to be looking at essentially any subset. But you're going to have to somehow look at the input, the C and the D, and be able to say, I'm searching in a tiny subset of all possible subsets. Okay, so this is something which should look amazing if you can do it, and it is indeed known. So I want to say immediately, this is NP hard. So it is NP hard to do this, to compute this opt. So the input is two matrices, and I ask you, what is this minimum? And if you want to do this, you're not going to succeed to do this in polynomial time unless P is equal to NP. Okay, so I'm asking for a goal which is impossible. Okay, and furthermore, it is also there exists some number epsilon 0 bigger than 0, which is a very concrete number. I just don't remember what it is. Maybe 1 over a million, probably 1 over 1,000. I simply don't remember what it is. Such that it is NP hard to compute this optimum number opt C of D up to factor 1 plus epsilon 0, whatever, some concrete number. So what do I mean by that? So I mean that I'm interested in the number that's written here. Okay, and so it is NP hard. There is no, okay, unless P is equal to NP, there is no algorithm that takes as input C and D and outputs a number which is, let's say, at least the opt, but at most 1 plus epsilon 0 times the opt. And epsilon 0 is some concrete number. By the way, I'm going to, because it's a 45-minute talk, I'm not going to be doing justice to history, and I'm not going to write lists of authors. All of these things are surveyed online, and references. I can give the relevant papers to anybody who wants. So the fact that you cannot do factor 1 plus epsilon 0 is a hard theorem. It's a substantial theorem, but I'm not new to me. But and that's one example of things that I will not give references. But everything, this is well surveyed online. Okay, so I asked you for a goal, and I just told you that the goal is impossible. It's actually a major challenge, which is open, and actually it attracted a lot of attention, is to prove that it is NP hard to do this, to compute opt. Up to any factor, any constant factor. I very much suspect that it's the case. There's very good evidence for it. So I should say this is known, assuming not P is equal not P is not equal to NP, but something called the Unigames conjecture. Which is a major conjecture in complexity theory, but it is not P is not equal to NP. So we do not know. So this is the limit. We do not know how to compute this opt, but we also don't really know to prove that it's not computable either. Now, why do we care so much? So recall so there was this universe, and the numbers 1 to n, This could be all of us who are listening to this talk. It could be all. It could be many data sets are just the numbers 1 to n. And the C's and the D's, remember these pairwise numbers, Cij and Dij, between I and j. The C's and the D's are some measurements of interaction. So if you can think Cij, if Cij is big, then I really likes j, or what? But there can be many interpretations. So what you have here is a universe of numbers, of elements, and measures of interactions between them. And what you're trying to do is you want to chop this universe into 2 pieces so that the relative interaction, the interaction relative to the C's is much less, or as less as possible, than the interaction relative to the D's. So with this degree of freedom, arbitrary C's and D's, you can encode numerous, I'm going to give 1 or 2 examples in a second, but numerous algorithmic tasks that we care about. And this type of chopping a universe into 2 pieces so that the 2 pieces have very little interaction, is little, hopefully, sometimes you can't, but I mean, if as little as possible, is a setup for a type of algorithm called the divide and conquer algorithm, which is a different way of saying induction, right? If you have some optimization problem on a universe of size 1 to n, what a natural thing to do is to try to prove it by induction. We want to chop it up into 2 pieces which are smaller, and then recurse. And if you want to glue these recursed solutions into a global solution, you want to make the interactions between the 2 pieces as small as possible. So there are really numerous instances of sparsest cut, depending on smart choices of weights, Cijs and Dijs, which encode many problems that we really are interested about in combinatorial optimization. So let me just give you one example, but this is really a very expressive general optimization problem that is, I would say, a central optimization problem in approximation algorithms. It received massive scrutiny over decades. So, for example, look at the case. Here's what's called uniform sparsest cut, an important special case, less expressive, but still important and very interesting, both geometrically and combinatorially. And that's the case when you take Cij are always 0 or 1. A priori, there could be any negative number. I'll say they can be only 0 or 1. And the Dijs are always 1. Okay, so what is it? So now what does it mean that the Cijs are 0 and 1? Remember, Cij is a symmetric matrix. So you can just draw, so here is your universe. And you so draw an edge between I and j if Cij equals 1 and 0 otherwise. And so saying Cij is 0 or 1 is the same as saying that we are given a graph, a combinatorial graph. Okay, and remember, what was the goal? The goal was to chop it up into 2 pieces and compute the total weight crossing the boundary in terms of the C's. What is that? That's simply the number of edges crossing the boundary. This is what's called the edge boundary of your subset S. And I also said that the case Dij is identically 1. The denominator is the sum of the Cijs when I is in S, j is not in S, of 1. Okay, so this is just the size of S times the size of the complement of S. You're just picking up I and j for every I in S and j not in S. There's nothing interesting going on with these. So this ratio that I started out with, this opt, is the number of edges crossing a boundary divided by morally the size of the boundary. It's the size of the boundary times the complement of the boundary. And the complement, the size of the boundary divided by the size of the set S times its complement. Okay, but it's this is the ratio of the number of edges to the size of the set up to a renormalization. Okay, So this is the edge boundary of a graph. You give a graph, compute the what's called the edge expansion of the graph. And for general C's and D's, this is what's called the conductance of this data. If, let's say, if there were symmetric stochastic matrices, this would be the conductance. So that's a special case. I'm going to say a few words. I'm going to say a lot about the general sparsest cut, which is the expressive problem, which we're going to discuss solutions of some natural questions about it. But the case of uniform sparsest cut, which is fascinating, is wide open. And if there are questions at the end, this is really, now that we understood the general case, there will be very tantalizing questions about this uniform case, which and then there are other special cases that I will get to in later. So, okay, okay, I will get to. There are other interesting special cases that I will get to at the end. Okay, so so this is the setup. I hope that there are that it's clear. It's very elementary. Anybody can understand. Most of the applications that appear online, there's a monograph of Schmoy's about divide and conquer algorithms, but there are many, many papers. Just search for sparsest cut. You're going to see it's used left and right. Most of these applications are for these inductive solutions, these divide and conquer algorithms. There are definitely more clever applications of this problem in combinatorial optimization. But most of them are in the scheme that I said. Try to solve optimization problems inductively. So you chop the universe into two pieces and you minimize the interaction between the two pieces. One other thing that I want to say is that, okay, it's very simple to describe, but so my background is in analysis and geometry. I'm very attracted to this because this is really about solving the most general isoperimetric problem you can imagine. It's a discrete version. You can imagine continuous versions of this, but when you allow general weights and C's and D's, you can encode, you can imagine this is a discretization of a very, very general type of isoperimetric problem. So isoperimetric minimizers proving that they're regular, the boundaries of if you want to chop a manifold or some other thing into small pieces, there is a lot of interest in showing that you do not take a general measurable subset, but you make the subset very, very nice. And to me, this feels similar to the desire of the optimization problem. We want to be able to search among a much, 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 much smaller class of partitions than what you would allow if you allow every subset. So a polynomial time algorithm will simply not look at essentially all the subsets. In the continuous mode regularity theorem, saying that the set has a smooth boundary, etc., also says that it's not a general crazy subset. We will see connections to analysis very soon, but I find this a very appealing question also from the analytic and geometric perspective. Okay, so let me first of all tell you, I'm going to discuss a little bit the interest, history, but let me tell you a headline that I want to work towards. So, as I said, the issue of computational complexity, NP hardness, even unique game hardness, is wide open. We do not know what to do. I think what's a very striking aspect of this particular question is this is a very central question in algorithms, in approximation algorithms. And in 1995, the best known algorithm for that was proposed. And it took until last year, so that's 30 years, to figure out what this specific algorithm does. So I'm going to write exactly what the algorithm is, but I'm going to say so mid-1990s, I don't know if 1995, mid-1990s, independently, Gomez and Lineal designed or proposed an algorithm. Let's call it GL for GL for Gomez and Lineal, an algorithm that outputs a number GL of CD, C and D, the two matrices were the input. It outputs a number that we call it GLC of D. It is always smaller in the way I'll formulate it than the opt. That will be automatic once we write it down. It's not a theorem. It's going to be self-evident. And then the goal and the hope was that it actually hits the mark. So I should have said the algorithm, this is polynomial time. So it takes the CD, it thinks, but not a lot. Outputs a non-negative number GLCD, which is always less than the opt. And then the goal is, let's call it what's called the integrality gap. So the goal, define rho GL of n to be the soup of, I want to make it a big number. So let's say, I want it to be, so it is going to be the soup of opt CD, what we really want, over what the algorithm, which I'm going to write what the algorithm is, just soup of this over all C and D on the negative symmetric n by n matrices. Okay. So this number is always at least 1 by design because of what I wrote. And the question is, well, hopefully it would have been a constant factor. Okay, but this number, rho GL, measures the performance of the algorithm, right? It does think polynomial time. How, if you can make this rho GL, it's what's it's small, then you succeeded to compute the opt up to a small factor. I hope this is clear to anybody. So I didn't say what the algorithm is, but this is for any algorithm. You're interested in this number. So that was done in the mid-1990s, and the theorem that I want to work towards is finished last year, is that rho GL n behaves, and by this I mean up to universal constant factors, 100,000 or so, some numbers independent of n, like root of log the size of the universe. Okay, so for many years it wasn't even known if it's bounded. We'll get to this. So, but the answer is that it does actually really, it does very well. It is, it will compute the minimizing partition, not exactly, but up to a factor of root log the size of the universe. And it has to make this large error sometimes. So there are two aspects here. There's an upper bound and a lower bound, and both of them are very interesting mathematically. So the upper bound is the upper bound. So upper bound. So rho GLN is less than root log n. When I write less or equal to twiddle, I really mean up to a universal constant dependent of n. So this is due to Chang, myself, and Ren from just last year. And the lower bound, rho GL of n, which is at least that log n is due to myself and Yang in 2018. So again, I am not gonna, there's a very long history. This is a very, very, very well-studied problem. And there are many, many papers and were intermediate bounds, etc. I'm not going to mention those. Everything is available online and surveyed very well. So so yes, again, what does the lower bound mean? I didn't write the algorithm yet, and I will. A lower bound means that you cook up an example of C's and D's on which you can prove that the algorithm messes up by at least this factor. And the upper bound, which is the very new result, which I will dedicate most of the talk to, is actually designing an algorithm. Oh, okay, the algorithm is given, but actually proving that the algorithm succeeds. Okay, so it's understanding something about the problem and saying, wait a minute, this algorithm is actually really, really good. And the fact that they match means that both of these theorems have to be very, very tight. You're not going to have any room for maneuver up to constants, both in the lower bound and the upper bound. Okay, so this is the 2020-25 headline, which is that this algorithm that was proposed, and I'm going to explain in a second, in the mid-1990s, now we know what it's actually doing. This does not address the question of what any algorithm does, the NP hardness. As I told you, our situation in terms of NP hardness is really, really, really much weaker. Okay, but this is a very natural geometric algorithm, which has a lot of meaning and a lot of connection to many, many areas of mathematics. This algorithm in itself took a long time to understand what it does. And this is not a minor corner. This was front and center. Understanding what this algorithm does was a very, very, very attention-grabbing problem that attracted a lot of work over the years. So that is the headline. I did not say what the algorithm is, so let me say what it is. Okay, but are there any questions about what my goal is? Okay. Are there any questions? So I can now.
Yeah, the question
Okay.
is the ratio OPT divided by GLE or GLE divided by OPT? And does GLE try to compute a small cut or what? That's the question.
This is I like to think about, I like to bound numbers that are big from above. This is just my preference. Of course, I could have done the opposite ratio and then prove to you that it's 1 over root log n. Okay. This is just, when I approximate something, I approximate it up to a small number, and proving that it's impossible to approximate means a big number is needed. So this is just a matter of taste. Okay. The algorithm is opt is what I care about, the numerator. Why is this not writing? Give me a second. So the numerator is what we care about. The denominator is something that I didn't say what it is yet, but it can be computed in polynomial time very efficiently. This number is always less than opt, which is the minimum possible partition. I'm always interested in the minimum possible partition. The minimum possible partition is encoded in opt. The algorithm will get something only smaller. And what we're saying here by bounding it from above is that it's not much smaller. And we know exactly how much. I know there are many people who prefer to look at 1 over, but this is not mathematics. It's just how you prefer to denote something. Okay, so for me, numbers tend to be big, and I try to bound them from above. They don't tend to be small, and I try to bound them from below. But if you prefer, then look at 1 over. I don't know if that was the question, but
okay, yeah, that was the question.
Okay,
yeah, that was
so
the
this is just a matter of preference. It's not there is no mathematics here. Okay. Okay, but I'm definitely within opt is the minimum, is the solving the isoperimetric problem. So the fact that I'm bounding this by root log n is I'm relating something very efficient to the actual solution of the general isoperimetric problem, which is hidden in the definition of opt. Okay, so I need to say what the algorithm is. Otherwise, why are we discussing this? And okay, so the algorithm is and this is so what I'm going to show you. So this is due to this approach. It goes back to Leighton and Rao in the late 1990s and 1980s. But the big step which connected this to very serious questions in analysis and geometry is due to Lineal, London, and Rabinovich. And Aumann and Rabbani. independently, both of these in the 1995, really exactly 1990s. So what I'm going to show you is the following. Okay, so remember what opt was. It was right. It was the sum. Sorry. It was the minimum of over all subsets of this sum Cij, I is in the subset, j is not in the subset, sum same Dij. I is in the subset, j is not in the subset. So let's look at this ratio, and let's write it. Okay, this is this ratio that I care about. I'm going to say something obvious, but is the same as saying the sum over all I and j, Cij. And now we take the indicator of the subset at I minus the indicator of the subset at j. And then the sum over all I and j minus. So that one subbase is just a function which is 1 if you're in the set, 0 if you're not in the set. So this is the same thing because I'm hitting Cij by a difference, which is exactly 1 when one of them is in the set and the other isn't. Right? So this is just rewriting it. So, so what we care about is the same as the minimum of all subsets of, now we have sum over all sets. It's just rewriting it. But now, this is I'll say it in a second. So it's the minimum of the following thing. So you run over all functions, f1 up to fn, in L1, let's say, of R. And I'll explain exactly what I mean. So this is equality. I didn't change anything. So L1 is just so L1 of R is just all the measurable functions from R to R, such that the integral f is finite, and this is the L1 norm of f. Okay, so if this is an equality, then okay, this is in essence this is a duality argument, or it's an application of the coarea formula. This function indicator s of I is an example of a function in L1. You can imagine the numbers, the real line, partition it into, look at the just intervals, any disjoint intervals of length 1, and just put 1 if the function is 0, except on the ith interval, you put 1. This is really the same thing. This is what's written in the numerator is an L1 norm. It's just a special case. So the minimum over all subsets or indicators of subsets is a special case of functions in L1. And there's a statement saying that the worst case happens for subsets. Okay, so in a class, I can give it as an exercise or just prove it, but this is what's called the cut cone decomposition, which is just a coarea formula or an instantiation of it. It says that the worst case is if you run over all functions in this massive function space is actually 0, 1 valued functions. The 0, 1, not the interval, the 0 or 1, the indicators of subsets. So I'm not saying this is obvious, but this is a classical fact that I think the first person who wrote it down was a Swad in the late 70s. And it's a nice fact that if there's time, if somebody will ask, I'll show the proof, but It's in textbooks. Okay, so but whenever you start with an NP hard quantity and you rewrite it as an equality, you made no progress because it's NP. It's equal. You didn't change anything. Okay, so now comes the idea of linear London and Rabinovich, which is do not minimize over functions in L1, but over all metric spaces. So first idea, this is called what's called the linear program. It's not linear. So now I'm going to interested in the following. Let's call it let's not give it a name. So I'm going to look at the minimum of some Cij Dij, capital Dij, Dij. And now the minimum is over all matrices Dij that are symmetric. I'm writing the axioms of being a metric space, a semi-metric space. And Dij is less than Dik plus Dkj. So this has to hold for all Ij and k. Okay. So clearly this minimum is less than opt CD, just because opt CD is equal to a special case of this. You can take Dij, you can define Dij to be Fi minus Fj. That's a perfectly legitimate instance of Dij. It satisfies. So in what's written here is just you minimize over more things. You forgot this is not a general metric space. This is not as endpoints in L1. It's endpoints in any metric space. Okay, so but this can be solved in polynomial. The left-hand side here can be solved in polynomial time. Right now it looks like a ratio, but you can also. This is the set, right? This is just normalization. I'm continuing here. This is the same minimum of some Cij Dij, given the same constraints, but add the constraint. It's just a normalization. Just add that the denominator is 1. And now look at what the variables Dij, they're also not negative, have to satisfy. So you're minimizing a linear function of variables d, little d sub ij, lowercase d sub ij. And the constraints required from these variables are that they're not negative. There's some identities here, but they're a linear equation. A whole n choose 3 for all triples. Linear inequalities plus another linear identity, which just normalizing the denominator. So this is minimizing a linear functional over some collection of linear inequalities. This you can do in polynomial time. Okay, you cannot do the original thing in polynomial time. That's a theorem that computing this opt exactly is NP hard. So by writing an identity here, I made no progress, but it gave me a hint, and we'll return to this hint. It gave me a hint, or it gave them a hint, of how to relax it. Okay? And so, is it clear that this is less than opt? But what's written in this squiggly line here is something that we can compute in polynomial time. And then, what they did in mid-1990s is they said they used the following great theorem called Bourgain's embedding theorem. Which was a decade 1985, which was done a decade earlier for a different purpose, which I'll see how much time it's very much related to how the solution will eventually be solved. But of course, Bourgain did not think at all about algorithms or Sparsest Cut. Bourgain's embedding theorem said that if you have done 1 up to n with D is a metric space, So if you define dij is what I call dij, then it satisfies the axioms I wrote before. Then you can cook up functions in L1 such that dij is at least fi minus fj, and at most some universal constant times log n times fi. So this is, if you give me an arbitrary endpoint metric space, you can cook up functions in L1 that represent, this is for all ij, that represent all pairwise distances up to a factor of log n. Okay, so Bourgain's theorem is the same as saying, so maybe you should give a name to this number. Call it the linear program, because this is linear constraints. So you can write the same thing, you define rho lin of n to be the ratio, the same thing as I wrote before, the ratio of opt divided by the minimum here. That's always at most log n, and this is just Bourgain's theorem. Okay, so we just proved that you can, that here a different, that there is an algorithm that finds the sparsest cut up to a factor log n. If you want to get the actual partition, you can also turn it into an algorithm, and they showed how to do it. But this is just about the number opt. Okay. So so this was what they did in 1995, and then the Goleman's linear algorithm is okay, remember I was interested in the minimum over all subsets sum Cij indicator of S of I minus indicator of S of J for sum Dij, same thing. And so what they propose is to do the following. So they compute the minimum of sum Cij Vi minus Vj 2 squared, given that V1 up to Vn are vectors in Rn, and if we define Vi minus Vj, this is a Euclidean distance. If you call this Dij, so it satisfies the triangle inequality. It satisfies the linear constraints. So Dij is less than Dik plus Dkj, and also the denominator is 1. Okay. So what we're doing is we're taking this linear inequality and we're doing a quadratic version of it. So let's stare at this for a moment. What is Vi minus Vj squared? That's Vi squared plus Vj squared minus twice the dot product of Vi Vj. So what's written in the thing I'm trying to minimize here is some linear function in entries of the gram matrix of Vi dot Vj. If you look at if you form the matrix Vi dot Vj, so the diagonal terms are the lengths of these Vi's, and the matrix is written there. So what's written here is some linear expression in the entries of a general symmetric positive definite matrix, because a gram matrix is a positive definite matrix. And the constraints are also a bunch of linear inequalities and equalities. Inequalities, also in the entries of a positive definite matrix. And the number is, okay, there is n through 3 here, and there is one more, so n to some unit, n cubed at most. Okay? So minimizing a linear functional in the entries of a positive definite matrix, given a bunch of linear inequalities in the entries of a positive definite matrix over all positive definite matrices, is what's called semi-definite programming. So this is a semi-definite program. And which can be, this is a substantial theorem. This is a big theory in algorithms that took a long time to develop, but it can be computed in polynomial time. So this quadratic, where did I write it? This minimum here, given these constraints, is a quadratic minimization problem, which does have a polynomial time algorithm. It uses the ellipsoid algorithm. What I'm telling you now is a substantial fact, but this is true. And this minimum is what I called rho, GL of C and D. You minimize the sum of Cij vi minus vj squared over all possible choices of vectors in Rn that satisfy these linear conditions and the entries of their gram matrix. So is the definition of GLC of D clear? It's a minimum of some quadratic term. Yes? And again, it's completely evident that GLC of D, the initial inequality that I wrote, is less than opt C of ND. Because opt C of ND in these quadratic terms here were just numbers which were either 0 or 1. With the indicator of S at I minus the indicators of S at J. And numbers which are either 0 or 1, you can square or not square, it's the same thing. Okay? So this is really just the previous expression. You go back to the previous expression, which is the original here, then just the definition. If you feel like, if you wish to, the number here is either 0 or 1, if you feel like it, square it. It doesn't change anything. And also it satisfies the triangle inequality by design, because it's square in power 1 is the same thing. So clearly you're minimizing over more things when you do this. So if you minimize over more things, you arrive at the original inequality, and rho GL was how small can this ratio be, or how big can the ratio of opt to GL be. So I just told you what the algorithm is. I did not tell you yet how to get the partition itself, but that is also part of the story. Everything I'm going to say is going to be, I'll discuss the number for simplicity, but I can also find the actual partition. And then, so this here is a theorem that requires a nice duality. This is what I think Rabinovich is the one who noticed this. So it says that rho GL N is equal to the smallest number K, such that for every V1 up to Vn in Rn, such that Vi minus Vj satisfies the triangle inequality, is a metric. There are functions F1 up to Fn in L1, such that Fi minus Fj is at most Dij and at most K times Fi. So you have to prove something here. So, right, you start with an arbitrary metric, not an arbitrary, a metric Dij, which satisfies this. Because of the identity that I wrote, that what I care about is the minimum over all functions in L1, I want to relate this back to L1, and this is just tight. So the smallest case such that you can realize this Dij is in terms of functions in L1 is just equal to how well this algorithm performs. So a different way to say what Dij is that the numbers one up to n with the metric Dij is a metric space such that the metric space square root of D is isometric to a subset of Hilbert space. And not Hilbert space of L1. Okay? This is a silly way to say the same thing because I define Dij to be the square of a Hilbertian distance. So I can take square root of this equation in that circle, and that's the square root of Dij equals Vi minus Vj. It's just a tautology, a different way to write. But that's important for the proofs, which I will not get to. So, so the theorem, the question is, so the theorem, as I said, which has two parts, which is this the performance of this algorithm is like root log n has two parts. Rho GLN, at least, this is myself and Young, is to find a metric whose square root is exactly a Hilbertian metric. Yet, if you want to realize it as functions in L1, you have to pay a factor of root log n. This is some impossibility statement. And so I'm going to say that the only example I know, and not for lack of trying, is related to interesting facts in geometric measure theory and geometric group theory. So this is the 5-dimensional Heisenberg group, which if there will be questions, I see I'm running out of time. I will tell exactly what the example is. And the funny thing is, and that was a surprise at the time, is that 3 dimensions are not enough. There is a counter example. So you need a 5-dimensional example to do this. And the upper bound is, right, we said rho GLN is less than root log n, is the same as saying for any. So this is a structure theorem for any, actually we prove for any metric such that the metric space is isometric to a subset of a Hilbert space, there exists F1 up to Fn in L1 such that, as I said, Fi minus Fj is less than Dij less than some constant root log n times Dij. So it's a structure theorem. It's a realization of an arbitrary geometry with this property, that the square root is in a Hilbert space. Up to root log n is a concrete n functions. Sorry, this is not Dij here. It's a typo. And actually, this is we can do this in L2, and that's actually Fj. So we can realize an arbitrary geometry like this as a subset up to root log n in a Hilbert space. Being in a Hilbert space is more stringent than being in L1, and that's useful for certain applications. So I will not have, but so what we're saying is, if you hand me any metric which has this property, you have to look at its structure. There's a smart way to partition it, etc. we can realize it up to root log n as a subset of Euclidean geometry. And again, root log n cannot be improved because of the lower bound. So I spoke much slower than I planned. I plan to show proofs of both the upper and lower bound. I will stop here. Everything is available online, and I will answer, of course, questions. So I guess whoever goes first, if somebody asks about what is the lower bound, what is the upper bound, that person will see it, because I'll at least explain what was going on. But I'm sorry I didn't get into the proofs, but I explained the connections. And in the end, this very, very complete optimization problem, it took since the mid-1990s, and this was not an unknown problem, this amount of time to solve it. And the proof uses interesting mathematics. In particular, 5-dimensional Heisenberg group shows up. And it does not work for the 3-dimensional, why even a Heisenberg group, etc. There are great questions about what happens in the case of abelian groups. There's still a lot to do in terms of these questions, even in the context of group theory. Okay. So I'm ready for questions.
Yeah, thank you very much for your talk. So everyone, I now allow everyone to unmute yourself. So you're welcome to unmute yourself. If you want, you can also show your face, share video, and you can type questions in chat, or you can ask in voice. So I think I will start, and I want to ask, so do you think this square root of log n is the optimal algorithm or not? Do you have any conjecture, prediction? Do you feel that it can be improved somehow?
Okay, so for what it's worth, I don't know what my feelings mean, but yes, I have a hunch just because I tried. But this doesn't mean much. I tried. I believe, whatever belief means, I expect that root log n is the truth also for a general algorithm. If somebody forced me to bet, I have no idea how to prove this. So this is about improving an NP. Okay, first of all, we do not know that P is not equal to NP. So you mean NP hardness, or assuming some hardness?
Yeah, of course.
Yeah, okay, so yes, if I were forced to make a prediction, I would predict that root log n is the truth for any algorithm, but it was even work for this algorithm. Those of you who know, there is some machinery out there for passing from semi-definite programming to hardness results. Maybe not NP hardness, but using something called the unigames conjecture. That machinery breaks down here. That machinery, to do Kot and Raghavendra, very, very nice things, really use that the approximation ratio is a constant. It doesn't go to infinity with n. So you can try to hope to take this 5-dimensional Heisenberg group example, plug it into the machinery, and crank out a hardness result, not NP hardness, unigames. But that machinery itself has to be enhanced, and I think enhanced substantially. But we have a beginning, which is with a lower bound for us, a natural semi-definite program. So yes, I know where to start, and I don't know how to take the next step. But if you force me to guess, I would say root log n is the truth.
Yeah. Okay, thank you. Do you want to click on the chat button yourself, or do you want me to read? If there is a chat button, you can use your computer.
One second. Let me see. Let's see if it works. Okay, I clicked on it. So where are we?
Yes, just the last message, if you read.
A high order of conductance. Yes, you can ask the question. Of course, I agree completely. What I said doesn't apply to those. So yeah, there are natural higher, maybe more. Actually, when you go to higher order, there are more than one option of what conductance should be. What is and these are legitimate questions, and I don't know what to say about them, because I and the rest of us have been stuck for a long time in the graph set and in the pairwise. But of course, you can go to higher order. I completely agree, and it's very interesting. Yeah, I wish we had more time in our lives, right? Yeah.
I also wanted to ask: is this algorithm implemented? and yeah, available somewhere in computer algebra systems and whatever, so where I can actually enter my C, D, rate, press some button and see the output. Is there any place like that?
Okay, the very, very latest one is too new. So the answer is no, but I see no reason not. There are implementations, so the case of uniform demands, which I mentioned at the beginning, it's a beautiful story. There we do not know the answer. That's the fact that for uniform demands you can do root log n. This is due to it's a great, beautiful paper of Aurora, Rao, and Vazirani, and that has been implemented. And I think it could be. I'm not. It should be mechanical, but maybe not fun to adjust it to the general case now that we know the algorithm. But I don't have a place for you to stick in your CD and get the output. I can give you pointers to a special case, and that special case, just in the year or 8 months since this appeared in stock of last June, to the best of my knowledge, nobody implemented this or did a variant of what's available online. So I don't see any issue, and but I'm not the one who did it, and I don't know of anyone who did it yet. But it's very close. I don't anticipate this to be too hard.
Yeah, I just want to comment that I read everywhere that the recent AI systems becomes very strong in implementations, in coding and whatever. So maybe because this is a so important problem, and so maybe with the help of AI, we finally will get this implementation and can really practically compute this up to square root of log n, not just in theory. Anyway,
absolutely, yeah. I completely agree. I think that the hurdle of it's unpleasant to implement goes away, so it can be faster. Yes, I completely agree.
Okay.
But again, this is technical. Nothing. All I'm trying to say is that nothing in these proofs is not very, very constructive, and any of us, just you go step by step, you know exactly what should be done. There is no magic happening there. The proofs are very concrete. So there is no moral reason why it should not be easily implementable, but tedious.
But it's not about the proofs, it's about the algorithm itself, yes.
Yeah.
The proof can be arbitrarily complicated, but the algorithm itself
is... then that's a semi-definite program. Then semi-definite solvers are available. You would want in that case... Okay, there are two things here, right? There is the number opt of C of D. But most practitioners, including, would want to also find the subset that demonstrates it.
Mm-hmm.
So the algorithm I just told you right now was how to get the number. In the proof, there's also construction of the subset. That's what I was referring to.
Of course.
Okay?
Yes.
Okay. So I was imagining that you want
the
actual partition. If you actually want to implement this and partition the universe into two parts, then you want not just to bound the number, but you want to actually get a subset. That is what will require implementation. Otherwise, I wrote down the algorithm and you can stick it into. Of course, you can. You should not take a general purpose semi-definite solver and do time-saving tricks for this particular setting. But yeah, I can give you places to stick this if you just care about the number. But algorithms, I would guess, would want the set, not just the number.
Yeah.
And we get the set. That's all I'm saying. It's just going to be tedious.
Yeah. Okay. Yeah. Thank you very much. Thank you very much for agreeing to talk. Thank you for nice talk. And thank you everyone for coming today. Yeah.
Thank you.